5 joules. On a rough table, therefore, most of the kinetic energy of the white ball is lost through friction. Less than half is transferred to the purple ball. So if we look at this, energy change for the white ball is as follows. Okay, the kinetic energy final, which again is still 0, minus kinetic energy initial, which is 5, is going to be negative 5 joules. So that's the total change in energy. Well, there are two different types of energy. There's work, and then there's the heat. So kinetic energy transfer to the purple ball is negative 3 joules. So there's a lot less work being done here because a lot more energy was lost because of the friction. Why was it lost? So much more energy was lost because of the friction? It's because it was a rough table. Okay, so it's not going to travel as fast. It's not going to hit as hard if your table is rough. So the kinetic energy lost as heat is Q equals negative 2.0 joules. Okay, that's what we got. So the total amount of change in energy is 5 joules. Okay, so how do we get this W, if you may ask? Okay, so first of all, we know it's going to be negative. Why? Because there's work done by the system. We ended up with 0 joules, and so we know it's going to be negative. So what we do is we take the kinetic energy collision and and subtract it from what we started with, right? We subtract the final from the initial, so we take 2, subtract 5, and that gives us negative 3. Well, to find the Q, we take the 3 minus the 5, and that gives us negative 2. Okay, and that gives us a total of negative 2. So in contrast, on a rough, poor quality table, the ball loses much of its initial kinetic energy as heat, leaving only a relatively small amount available for work. Notice that the respective amounts of energy converted to heat and work depend on the details of the pool table and the path taken, while the change of the internal energy of the rolling ball does not. Because internal energy is a state function, the value of energy for the process in which the ball moves across the table, collides with another ball, depends only on the ball's initial and final kinetic energy. Work and heat, however, are not state functions. Therefore, the values of Q and W depend on the details of the ball's journey across the table. On the smooth table, W is greater in magnitude than Q. On the rough table, Q is greater in magnitude than W. However, the change in energy is the same. Okay, so looking back at this one, on the smooth table, our Q and our W, here, let me change. So our W and our Q were different. Okay, so on our smooth table, our work was a lot more than our heat lost. So our work, it was able to do a lot more work to the purple ball because not a lot of energy was lost because of friction. Well, on this table, a lot more energy was lost because of friction, despite how much work was done. So the amount of work done is still going to be greater, but you had a lot more energy lost because of the rough table. But notice their change in energy is still the same, okay? Because the amount of energy we started off with was still the same, and the amount of energy, therefore the amount of energy that we end up with has to be the same, okay? And so what that means is that the change in energy is a state function. Doesn't matter how we got there, we still got the same amount of energy for both of these, for the smooth table and for the rough table. But work and heat are not state functions. Therefore, they can change, but as long as the amount of energy ended up with is the same. Okay? And so, in the previous billiard ball example, the change in energy of the white ball is the same for both cases, but Q and W are not. On the rougher table, the heat loss Q is greater. Q is a more negative number. But on the rougher table, less kinetic energy is transferred to the purple ball, so the work done by the white ball is less. Because, by the time the white ball gets to the purple ball, a lot of this energy is absorbed by the table. The change in energy is a state function that depends only on the velocity of the white ball before and after the collision. In both cases, it started off with 5 kilojoules of kinetic energy and ended up with 0 kilojoules because it stopped. Q and W is the same for both tables, even though the values of Q and W are different. Okay? So let's look at an example. A potato cannon provides a good example of heat and work associated with chemical reaction. In a potato cannon, a potato is stuffed into a long cylinder and is capped on one end and open on the other. Some kind of fuel is introduced under the potato at the capped end, usually through a small hole, and ignited. The potato shoots out of the cannon, sometimes flying hundreds of feet, and the cannon emits heat into the surroundings. So it's emitting heat into the surroundings. So that should tell us that our change in E should probably be negative, right? If the burning of the fuel performs 855 joules of work on the potato and produces 1422 joules of heat, what is the change of energy for the burning fuel? Note, a potato cannon can be dangerous and should not be constructed without proper training and experience. Okay, so to solve the problem, substitute the values of Q and W in the equation for change in energy. Since the work is done by the system on the surroundings, the W is going to be negative. Similarly, because the heat is released by the systems to the surroundings, Q is also negative. Okay, so the reason that W is negative is because work is done by the system. Okay, what's happening? It's shooting the potato. Similarly, because heat is released by the system to the surroundings, heat is released by the system to the surroundings, Q is also negative. So here's our formula. Change in energy equals Q plus W. And so our Q is negative and our W is negative. Therefore, our answer is also going to be negative. 22,277 joules. Okay, so a cylinder and piston assembly defined as the system is warmed by an external flame. Okay, think about what's happening here. An external flame is warming the system, right? The contents of the cylinder expand, doing work on the surroundings by pushing the piston outward against the external pressure. Doing work on the surroundings. If the system absorbs 559 joules of heat and does 488 joules of work during the expansion, what is the value of change in E? Okay, so let's look at this. The system is absorbing joules of heat, but what also happens? It does work during the expansion. Okay, so the system is doing work. Therefore, the system is doing work. Therefore, our work is going to be negative. But what's happening with the heat? It's absorbing heat. Okay, that means that Q is going to be positive. Okay, so the change in energy equals Q plus W. That equals Q, which is the amount of heat absorbed, which is 559 joules, plus W, which is the work done by the system, which we know it's going to be negative 488 joules. Okay, this unit is very important to keywords. Okay, the system is absorbing heat, it's doing work. Okay, so it's very important that you understand these words. So 559 plus negative 488, And that gives us the change in energy is going to be 71 joules. Notice it's positive. That's because the amount of energy absorbed, or the Q, is